All right, let's dive right into this explainer. Today, we're looking at the absolute bleeding edge of materials science and medicine. We're focusing on a major, game-changing breakthrough that is completely rethinking how we interact with the human body on a molecular level. Whether it's regenerating a failing joint or healing a severe burn, the real-world stakes here are massive, and the materials we're discussing today are literally at the very heart of making that kind of healing possible.
So, here's the massive question keeping researchers up at night. How do we actually build better human tissue? Especially when we're trying to deliver drugs with pinpoint precision, or trying to help the body regenerate damaged areas like skin or cartilage. For a long time, researchers have been hunting for a material that is structurally tough enough to hold up inside the body, but biologically friendly enough that our own cells actually, want to interact with it.
Well, to crack this, researchers turned to something called hybrid nanocomposite hydrogels. Now, I know that's a mouthful, but essentially, picture microscopic, water-loving nets that physically trap or chemically link to specific therapeutic nanoparticles. Imagine a continuous 3D sponge that can be loaded up with functional nano-objects, like organic or metallic particles, that are designed for highly controlled, localized drug delivery. The continuous polymer phase acts as the main structural framework, and picking the right material for this framework basically dictates everything from how the gel swells to how it eventually degrades.
Section 1. The natural polymer matrix.
Now, the foundation of these hydrogel nets has to be built out of something, right? And if we look to natural materials derived right from biological environments, like plants, animals, and microbes, we get nature's own building blocks, specialized polysaccharides. Take capsaicin, for instance. It brings this built-in natural antimicrobial edge and a ton of structural flexibility, which makes it a fantastic host for loading up functional nano-objects. Alginate, on the flip side, can rapidly form a network using just mild calcium ions. And then you have hyaluronic acid. This one is super cool because it's a vital component of our own native extracellular matrix. Our body's native enzymes can actually break it down precisely, and scientists frequently modify it to create these dynamic, self-healing networks that really support cell viability.
And nature's toolkit doesn't stop there. We've got highly targeted materials like dextran, which is specifically great at supporting dermal regeneration and skin cell growth. There's chondroitin sulfate, which naturally brings anti-inflammatory and cartilage-restoring properties to the table. And we definitely can't forget structural proteins like collagen and its denatured cousin, gelatin. These contain absolutely crucial RGD sequences. You can think of these sequences as chemical welcome mats that actively guide our cells to migrate, recognize the material, and signal for tissue reconstruction.
But here's the catch, and it's a big one. While these natural matrices beautifully mimic the human body and are highly biocompatible, they suffer from physical fragility and completely unpredictable degradation under physiological stress. You simply can't rely on them alone because they have poor mechanical strength and low tensile thresholds. On top of that, because we extract them from biological sources, you get notable batch-to-batch structural variability. You just can't always predict exactly how quickly they'll break down in a living system. And actually, in the case of alginate, mammalian systems entirely lack the built-in enzymes needed to naturally break down its heavier molecules over the long term.
Section 2. The synthetic polymer matrix.
Since those natural materials can be a bit too weak and unpredictable on their own, polymer chemists hit the lab and turn to our second set of players, synthetic matrices. These lab-made marvels are designed for extreme structural control, precision, and most importantly, reproducibility. Take PEG, for example. It acts as a highly hydrophilic stealth macromolecule. It essentially hides from the immune system while allowing its chain ends to be perfectly tailored for covalently linking to nanoparticles. Then you've got polymers like PVA and PAA. These can withstand massive shape deformation, giving you exceptional stretch and shape retention even under high-stress conditions. And for super durable elastomers, polyurethanes can even be engineered using sustainable green synthesis to keep toxic residues entirely out of the picture.
To really wrap your head around the power of these synthetics, consider a very specific number, 37 degrees Celsius, normal human body temperature. Scientists have engineered these incredibly clever stimuli-responsive block copolymers, like PLGA-PEG-PLGA, that actually undergo a phase shift right at this exact temperature. That means a doctor can easily inject it as a liquid, and then it spontaneously solidifies into a stable gel right where the therapeutic nano-objects are needed. How cool is that?
Okay, so problem solved, right? Well, not quite. Just like natural polymers, synthetics have their own fatal flaw. They are entirely bioinert.
That means they completely lack those natural peptide motifs that cells need to actually recognize them. They offer virtually zero intrinsic cellular adhesion sequences. So, to a living cell, a purely synthetic hydrogel is just a completely foreign, biologically blind object. Furthermore, if the chemists don't perfectly engineer how the network breaks down, they can sometimes leave behind acidic or toxic degradation fragments that just build up in the body.
Section 3. The Great Divide: Natural versus Synthetic. We are basically looking at a classic Goldilocks problem here, where neither extreme is quite right on its own. Pitting them head-to-head, we see this stark dichotomy. One side is biologically fluent but structurally weak, while the other is virtually indestructible but biologically totally blind. Monolithic, natural, continuous phases, or entirely synthetic ones, rarely satisfy those dual prerequisites of biological recognition and physical longevity at the same time. You either get a structure that cells absolutely love but immediately shatters under physical stress, or a structure that lasts forever but cells flat out refuse to integrate with.
Which leads us to the grand finale, Section 4, the biohybrid solution.
Let's see how modern research actually solves this massive medical puzzle. Instead of forcing a choice between the two extremes, scientists simply merge them. They create a single network biohybrid configuration, which is essentially the ultimate equation for modern biomaterials. By integrating natural polymer components right alongside synthetic polymer chains, they harness the distinct advantages of both worlds while completely neutralizing their limitations.
Think of it as the ultimate tag team. The synthetic backbone acts as the heavy lifter. It provides this precise, predictable host that controls the cross-linking density and anchors the physical network against the body's stresses. And because of that robust structural longevity, the natural polymer is free to safely and steadily deploy its biological motifs, like those vital RGD welcome mats we talked about, to actively direct cell migration, encourage cell signaling, and actually reconstruct the damaged tissue from the inside out. It is a wildly elegant compromise that finally satisfies both the mechanical and biological demands of the human body. So with this perfect recipe finally unlocked, it really makes you wonder just how far this biohybrid technology is going to take the future of human healing and targeted medicine. We've literally bridged the gap between the rigid precision of laboratory chemistry and the complex, beautiful reality of human biology. As these hybrid nanocomposite hydrogels become more advanced, capable of delivering highly specific nanomedicines directly to a tumor or flawlessly regenerating severe skin wounds, we aren't just treating the body anymore. We are literally teaching it how to rebuild itself. What other impossibilities will this unlock next? Thank you for joining me for this explainer, and I hope you're walking away with a brand new appreciation for the incredible biomaterials shaping our future.